Hello all. It is Navanila Krishnan from iitiansgateclasses, Bangalore, who is going to handle flight mechanics in GATE Aerospace syllabus. Today's topic which we are going to discuss is turning flight performance from accelerated flight. Turning flight performance is the case where we deal with radial acceleration, that is curved flight path. Turning flight performance of an airplane has three cases: level turn, pull up maneuver, pull down maneuver. Level turn is just a curved flight path in an horizontal plane parallel to the plane of ground. That is, in a level turn, the altitude remains constant. This is the front view of the level turn, where aircraft is banked to an angle pi, where lift vector is tilted at an angle pi. This is the front view of the airplane. In top view, the airplane looks like this. That is, airplane is going in a circular motion in a constant altitude. In this, the airplane is banked at an angle pi, where lift vector is tilted. From this figure, we can resolve our forces as, if we take the vertical axis, if we resolve forces in vertical axis, what happens is my force becomes L cos pi, that is equal to weight. Okay, that is what happens here is towards the angle is cos, so when I resolve towards the angle, it becomes L cos pi equal to weight, because they are opposite to each. That is our first equation. From that equation, we can obtain load factor is equal to L by W. We know that load factor is equal to L by W. From this equation, L by W is nothing but 1 divided by cos pi, that is equal to secant pi. Load factor for a steady level flight is nothing but equal to 1, because lift is equal to weight. But for the maneuvering flight, here you have seen that n is equal to secant pi. Secant pi is always greater than 1. So for maneuvering flight, load factor is always greater than 1. When we are going in a curved flight path, what happens is, since the lift vector is acting at an angle, there is always a resultant force acting. This resultant force which leads to a curved flight path. Causing the airplane to go in a circular path. Like this. So, in this figure, all lift, weight and resultant force is shown in a vectorial representation. So, if I bring this lift here, what happens is, it's shown in a vectorial representation like this. Okay, so that figure can be remodified as like this: lift which is acting at an angle pi to the vertical axis, resultant force which is acting inward to the horizontal, perpendicular to the horizontal plane, and weight which is acting perpendicularly downward. From this, from this figure, using Pythagoras theorem, we can rewrite as lift square, that is hypotenuse square, equal to sum of adjacent square. That is lift square equal to W square plus FR square, that is resultant force square. If I rearrange, we can rewrite it as FR equal to square root of L square minus W square. If I take W from this square root, if I take W outside of this square root, what happens is, my equation becomes as W into root of L square by W square minus 1. L by W is nothing but your load factor. When I substitute that, resultant force becomes as W into root of n square minus 1. Since we are going in a curved flight path, the radial acceleration is given by v square by r. From Newton's second law of motion, the resultant force is equal to mass into centripetal acceleration. That is your radial acceleration, v square by r. Mass can be written as weight divided by acceleration due to gravity. Because mass is given in kilogram, when we are converting in terms of weight, it is W by acceleration due to gravity into v square by r. From the above figure, from the first figure, the resultant force can be also written as L sin pi. L sin pi is lift to away from the angle is sine. So L sin pi is equal to resultant force. That is what given in this equation. L sin pi. Resultant force equal to L sin pi. When we equate these two equations, what happens is W into root of n square minus 1 equal to W by G into V square by R. From that, we can write radius of turn as V square by G into root of n square minus 1. This is the turn radius. To obtain smallest possible turn radius, that is, if r to be small, to obtain r to be small, velocity should be maximum and velocity should be minimum and load factor should be maximum. That is, to obtain smallest possible turn radius, we require highest possible load factor and lowest possible velocity. Turn rate is nothing but d psi by dt. Omega is the turn rate, which is simply the local angular velocity of the airplane, which is given by v by r. That is linear velocity by radius of turn. That is, turn rate is nothing but d psi by dt, which is nothing but v by r. That is linear velocity by radius of turn. From that, we already derived radius of turn equal to v square by g into root of n square minus 1. When we substitute that, our turn rate becomes as g into root of n square minus 1 by v infinity. In order to obtain largest possible turn rate, we should have highest possible load factor and lowest possible velocity. That is, to have a smaller turn radius and to have a larger turn rate, we should have highest possible load factor and lowest possible velocity. Next turning flight is pull-up maneuver. That is, aircraft was going in a straight and level flight where lift is balanced by weight. Suddenly, it is going in a pull-up maneuver. That is, suddenly it is getting accelerated and it is going into a pull-up maneuver where lift increases and it tends towards the resultant force, which makes it to go to a curved path. The resultant force acting on this airplane is lift minus W, L minus W. When I take W from this common, it becomes as W into L by W minus 1. L by W is nothing but your load factor. So my equation becomes as W into N minus 1. From Newton's second law of motion, the resultant force equal to mass into radial acceleration or centripetal acceleration. That is equal to mass into V square by R. Mass can be rewritten as W by G, weight by, divided by acceleration due to gravity, into V square by R is the resultant force. By equating these two equations, my turn radius becomes as V square by G into N minus 1. From the definition of turn rate, that is the angular velocity, which is the local angular velocity of the airplane. Turn rate is equal to V infinity by R, that is linear velocity by R. So, substituting R in this equation, turn rate becomes as g into n minus 1 by linear velocity, v, that is flight velocity, v infinity. In a pull down manner, next is pull down maneuver. That is, aircraft is going in a straight and level flight. Suddenly it takes an inverted turn. Suddenly the airplane rolls and it is in the inverted position, where lift and weight is acting in the same direction. Thereby, this is the lift, this is weight. So lift and weight is acting in the same direction, same downward direction, which is causing the airplane to go in a downward circular path. The resultant force acting on this airplane is lift plus weight. So lift plus weight. So if I take W common, my equation becomes as W into n plus 1. From Newton's second law of motion, the resultant force is nothing but mass into radial acceleration. The radial acceleration is nothing but v square by r. Mass can be written as weight divided by acceleration due to gravity. When we equate this both equation, what happens is it becomes as w into n plus 1 equal to w by g into v square by r. From this, radius of turn can be written as r equal to v square by g into n plus 1. From the definition of turn rate is nothing but your local angular velocity of the airplane, that is equal to v infinity by r. So when I substitute turn radius in this equation, my equation becomes, turn rate becomes as g into n plus 1 by v infinity. Let us assume that we are in a high performance fighter aircraft, load factor is very, very large. When load factor is very, very large, we can assume that n plus 1 is approximately equal to n and n minus 1 is approximately equal to n. For such cases, the radius of turn and turn rate becomes as r equal to v square by g into n. Turn rate becomes as g into n by v infinity. Lift is nothing. Lift is given as half rho v square SCL. From that, velocity square can be written as 2L divided by rho SCL. Lift is nothing but load factor into weight. So substituting that, my equation becomes as 2NW by G into rho SCL. Substituting v square in this equation, we get radius of turn as 2W by G into rho SCL. Now, substituting root of v from this equation, in this equation, we get turn rate as G into root of rho CLN divided by 2 W by S. W by S is the wing loading. If you compare this both equation, like if we see this radius of turn and turn rate equation, in order to have a small turn radius, wing loading should be minimum. In order to have a larger turn rate, wing loading should be minimum. With lower wing loading, we can have a smaller turn radius and larger turn rate. One more thing is, from this equation, for turn radius to be minimum, CL should be maximum. For turn radius to be minimum, CL should be maximum. For turn rate to be maximum, CL should be maximum. Okay. In this, load factor is also there. From load factor is nothing but lift divided by weight. Lift is nothing but half rho v square SCL divided by weight. Load factor maximum is nothing but CL maximum. So for turn rate to be maximum, CL should be maximum. These are the remarks which you obtain from this following equations. That is, to have a smaller turn radius and larger turn rates, wing loading should be minimum and CL should be maximum. We'll solve few problems of gate. Excuse me. We'll solve few problems in GATE in this section. GATE 2008, question number 7. In a steady level turning flight of an aircraft at a load factor n, the ratio of horizontal component of lift and aircraft weight is option A root of n minus 1, option B root of n plus 1, option C root of n square minus 1, option D root of n square plus 1. So what is this? We are in a level turn flight. From the level, this is the level turn flight's front view. That is, lift is banked at aircraft is banked at an angle pi, so that lift vector is tilted to an angle pi. From this, L cos pi is equal to W. L cos pi equal to W. From this, load factor can be written as lift divided by weight. Lift divided weight can be equal to 1 divided by cos pi. Lift divided by weight equal to 1 divided by cos pi. That is equal to secant pi. So n is equal to secant pi. Load factor is nothing but secant pi. What they asked, the ratio of horizontal component of lift and aircraft weight. What is the horizontal component of lift? It is nothing but L sin pi. This is the horizontal component of lift. So L sin pi divided by weight is nothing but L by W is nothing but n. Sin pi is sin pi. From the trigonometric relation, sin square pi plus cos square pi equal to 1, where sin square pi can be written as 1 minus cos square pi. If I take cos square pi common from this relation, my equation becomes as 1 divided by cos square pi minus 1. 1 divided by cos square pi is nothing but your secant square pi minus 1, where secant pi is nothing but your load factor n. So n square minus 1. So sin pi is nothing but cos pi into root of n square minus 1. Substituting this in this above equation, my equation becomes as n cos pi into root of n square minus 1. Cos pi is nothing but 1 by n, because secant pi equal to n means cos pi is nothing but 1 divided by n. So if I substitute cos pi as 1 divided by n, my equation n is cancelled. So horizontal component of lift divided by weight becomes as root of n square minus 1. Okay, root of n square minus 1. This is root of n square minus 1. So what is the option? Option C is the correct answer. That is, the ratio of horizontal component of lift divided by aircraft weight is root of n square minus 1. Next, GATE 2011, question number 39. An aircraft in a steady level flight at a forward speed of 50 meters per second suddenly rolls by an 180 degree and becomes inverted. If no other changes are made to the configuration or controls of the aircraft, the nature of the subsequent flight taken by the aircraft and its characteristics parameters. Assume G equal to 9.81 meter per second square R. Option A, straight line path with a speed of 50 meter per second. Option B, upward circular path with a speed of 50 meter per second and radius of 127.4 meter. Downward circular path, option C is downward circular path with a speed of 50 meter per second and radius of 127.4 meter. Option D, downward circular path with a speed of 25 meter per second and radius of 254.8 meter. Here in this option, it is not meter per second, it is meter. Okay. That is, aircraft was going in a steady and level flight. Suddenly, it took in a turn. Suddenly, it is inverted. So, lift and weight is acting in the same direction, which means the resultant force is acting downward, which means it is taking a downward circular path. So, only option C and D might be correct from this. Is correct from this option. So, which is the correct option? We'll see. That is, aircraft suddenly taken an inverted flight, that is inverted turn 180 degree, so that the resultant force is acting downward, thereby it is taking a downward circular path. That is, it is undergoing a pull down maneuver. From pull down maneuver, we know that resultant force is nothing but lift plus weight. From that, that is, from the pull down maneuver, we know that radius of turn for the pull down maneuver is nothing but v square by g into n plus 1. Substituting v equal to 50 meter per second and g equal to 9.81. That is, initially it was in a level flight. It taken into an inverted turn. That's it. So for a level flight, load factor is nothing but 1. So substituting load factor equal to 1, my turn radius becomes as 127.42 meter, approximately 127.4 meter. Hence, from the given option, option C is the correct answer. That is, it is going into a downward circular path with a speed of 50 meter per second and radius of 127.4 meter. With this, I'll wind up today's section. Thank you.